In this lecture, we'll look at structured data and relational databases, the structured query language, SQL. We'll look at SQL and PySpark joins, and we'll look at broadcast variables and accumulators. Recall that we've talked about two key data management concepts. The first being a data model, which is a collection of concepts for describing data. The second is a schema, which provides a description of the particular collection of the data using a given data model. Now, conventional wisdom is that only 20% of data is structured, and even this number is decreasing because of the rise of consumer applications, enterprise search, and media applications. All of these generate data that is primarily semi-structured or unstructured. In this lecture, we will look at structured data, where we have a specified schema that we start with, and then we look at the data itself. In a relational database, we have the following definitions. First of all, a relational database is a set of relations, and there are two parts to a relation. A schema that specifies the name of the relation plus each column's name and type. So here we have a schema for a relation called students, and it consists of columns of a SID, name, email, age, and GPA, and each of those columns has an associated type. For example, the name is type string, the GPA is type real. The second part to a relation is an instance, and this is the actual data at any given time. And this has two characteristics. The first is the cardinality, or the number of rows, and the second is the degree or number of fields in that instance. Now we can add to our key data management concepts a third concept, which is a relational data model. And this is the most used data model. A relation is a table with rows and columns, and every relation has a schema that defines the fields in the columns. A database is a large organized collection of data, and transactions are used to modify that data. Now, databases model real world, like enterprises, and so we have things like entities, such as teams and games, and relationships in a database. So we can say, for example, the entity A plays against the entity B in the World Cup, where plays against is the relationship. Here are some examples of large databases. The United States Internal Revenue Service has a database consisting of 150 terabytes worth of taxpayer records. The Australian Bureau of Statistics has over 250 terabytes worth of vital statistics about Australians. And AT&T has over 312 terabytes worth of call records for all of its callers. eBay's database, its largest database, is over 1.4 petabytes in size. And Yahoo has a click database that's used for behavioral tracking that contains over 2 petabytes worth of data. Now, for each of these large databases, we can ask the question, what matters for these databases? In the case of the IRS, they care about accuracy, consistency, durability, and the ability to make rich queries. The Australian Bureau of Statistics cares about fast, rich queries. AT&T, for their call records database, cares about accuracy, consistency, and durability. eBay and Yahoo care about availability and timeliness for their databases. Here's an example of an instance of a student's relation. The schema is the one that we saw earlier, which is we have a student ID, we have a name, we have a login, an age, and a GPA, and associated with each one of those columns is a type. In the instance we see here, we have 3 rows, so the cardinality of this instance is 3. And we have 5 columns, so the degree is 5. And you'll notice that all of the rows, the tuples, are distinct. Now, relational databases have several advantages. They provide a well-defined structure. They maintain indices which allow them to have very high performance. And they guarantee the consistency of the data is maintained by using transactions. The disadvantages of databases are that they have a limited, rigid structure, and that most of the disk space ends up being taken up by large indices. Transactions can also be very slow, and they have very poor support for sparse data. So you can see that many of the things that are advantages in one respect are also disadvantages in another respect. Now, looking at this last item, poor support for sparse data, in more detail, we find that sparse data is very common today. Oftentimes we want to store data with thousands of columns, but not all of the rows will have values for all of the columns. In a typical database, the tables might have dozens of columns, but tables are going to be very wasteful for sparse data because most of the entries are going to be empty. The structured query language, or SQL, is a language for relational databases. It's supported in PySpark by data frames. And some of the functionality that SQL provides is the ability to create, modify, and delete relations, to add, modify, and remove tuples, and to specify queries to find tuples matching criteria. Let's look at this last functionality item, specifying queries to find tuples that match a particular criteria. Single table queries are very straightforward in SQL. To find all 18-year-old students, we can write select star from students S, where s.age equals 18. If we just want to find the names and logins, we would write instead select s.name, select.login from students S, where s.age equals 18. We can specify a join over two tables as follows. We have the table enrolled E and students S, and we perform the following query. Select s.name and e.cid from students S and enrolled E, where s.sid equals e.sid. Now, the first thing that the system is going to do is to combine the two tables S and E. It's going to do this by performing a Cartesian product of the two tables. It'll do this by taking all of the rows from E and combining them with all of the rows from S. We will end up with the following table. The next step is to use the where clause to select matching rows. So in this case, it's where s.sid equals e.sid. We can see that there are two rows. The next step is to filter columns using the select clause. And the select clause here is s.name and e.cid. So now we're able to return the result, which is two tuples, Jones and History 105, and Smith and Physics 203. SQL allows you to explicitly state the type of join that you want to perform. So in this case, we have stated that we want to select s.name and e.classid from students S inner join enrolled E on s.sid equals e.sid. This is the same as what we saw earlier. It will combine the two tables, the Cartesian product, and then select those tuples where s.sid equals e.sid. Now, all of these are equivalent join notations, but the explicit versions are preferred. In the explicit case, we have the example that we just saw, select s.name and e.classid from students S inner join enrolled E on s.sid equals e.sid, or we can actually drop the keyword inner, as the default join is an inner join. Now, what we saw in the earlier example was implicit join notation, but this has since been deprecated, and so you shouldn't use it anymore. Instead, you should explicitly say either inner join or joined. SQL provides support for multiple types of joins. The type of the join controls how unmatched keys are handled. Here we have an inner join, and it's between two tables, students S and enrolled E. We can see in the table S that there's an unmatched key brown, and we can see in the table E that there's an unmatched key for English 10. When producing the result, an inner join will not include any tuples for which there is not a matching key in the other relation. The second type that we want to look at is a left outer join. With a left outer join, if a key appears in the left table, in this case students S, but not in the right table, in this case enrolled E, then the key is included, but with the value null. So in this case, Brown appears in the result, but with a class ID that's null. The third and last case that we can look at is a right outer join. With a right outer join, if a key appears in the right table, in this case enrolled E, but not in the left table, in this case students S, then the key is included, but with the value null. So in this case, English 10 is included as the class ID, but the name is null. Spark supports joins in two ways. Spark SQL and Spark data frames support inner, outer, left outer, right outer, and semi-join operations. For pair RDDs, PySpark supports inner join, left outer join, right outer join, and full outer join. Here's an example of how pair RDDs support joins. x.join_y will return an RDD containing all pairs of elements with matching keys in x and y. Each pair will be of the form k and v1, v2 as a tuple, where kv1 is in x and kv2 is in y. So here we have an example of two collections. We have a collection that contains A and Y as a pair, along with B and 4 as a pair, and a second collection that contains A and 2 as a pair, and A and 3 as a pair. When we perform a join, the result will be a collection consisting of A and the pair 1, 2, because 1 appears in X and 2 appears in Y, and A and the pair 1 and 3, because A1 appears in X and A3 appears in Y. Notice that B does not appear in the output, because B only appears in X, not in Y. Here we have a left outer join, which has the property that for each element KV in X, the resulting RDD will contain either all pairs K and the pair VW for W in Y, or the pair K and V along with none if no elements in Y have the key K. So as the example, we have A and 1 as a pair and B and 4 as a pair, and we have a relation consisting of A and 2 as a pair. So when we do the left outer join, the result will be the pair A and the pair 1, 2, because 1 appears in X and 2 appears in Y with A, and the pair B along with 4 and none, because 4 comes from X and B only appears in X and not in Y. With a right outer join, each element KW in Y will result in an RDD containing all pairs of K and the pair VW for V in X, or the pair K and none and W if no elements in X have the key K. So in this case, we start with A and 1 as a pair and B and 4 as a pair in X, and A and 2 as a pair in Y. Now when we perform our left outer join, we'll end up with the result A and 2, 1, because 2 appears in Y and 1 appears in X, both with A, and B along with none, 4, because B appears in X but not in Y. The last join is a full outer join, and for each element KV in X, the resulting RDD will either contain all pairs of K and the pair VW for W in Y, or K and the pair V and none if no elements in Y have K. It'll also contain, for all elements KV in Y, all pairs K and the pair VW for V and X, or K and the pair none, and w if no elements in X have K. So that's a little complicated. Let's actually look at an example. So here we have one collection consisting of the pair A and 1 and B and 4, and a second collection consisting of A and 2 and C and 8. When we produce the full outer join, we'll end up with A with the pair 1 and 2, because A appears both in X and in Y. We'll end up with the pair B and 4 along with none, because B only appears in X with the value 4. And then finally, we'll end up with the pair C and the pair none and 8, because C only appears in Y and not in X, and it appears with the value 8.